Yes, class. Good evening. I hope I'm audible to all of you.
Yes,
Good
ma'am.
evening, ma'am. Yes, ma'am.
All right. So, Eram, Tarif, Abdullah, Tareem. Who is this? Sayyada Safura?
Ma'am, I joined recently.
Okay. This is your first class today.
Yes, ma'am.
All right, Safura. So, how many lessons have been covered in your school?
Ma'am, the first textbook is over.
First book is over. Okay.
Yes.
So, Safura, see, you just have to have a little patience for today's class because rotational motion, no, we are towards the end of rotational motion. So, today is the last class for it. So, in the next class, that is Wednesday on the same timings, we are going to have our next class for starting from the next chapter. So, gravitation will start on a fresh note. So, I think you will be able to understand from there. For today's class, it will be a revision for you. And otherwise on Fridays, we are having the backups from rest of the chapters. So for rest of the lessons, you can keep on taking the backup classes I'll discuss on Wednesday. But for the meantime, just wherever you're not able to understand anything, let me know. Otherwise, this is just end of rotation motion. Fine?
Okay, ma'am.
All right. So yes, class, in the last class, we have seen the dynamics of rotation motion. Wherever you had force, you substitute torque. Wherever you have mass, you substitute moment of inertia. For displacement, you have angular displacement, that is theta. For velocity, you have angular velocity omega. For acceleration, you have angular acceleration alpha. Linear momentum, here it became the angular momentum. Rest of the things I think we have discussed. So whatever formula you have in case of linear motion, just convert it as it is for rotational motion. Now, conservation of angular momentum we have done. Yes, we have done conservation of angular momentum. If external torque is zero in your system, if external torque is zero, then rate of change of angular momentum is also zero, because torque is basically rate of change of angular momentum. So angular momentum remains constant. That is, I omega is constant. I1 omega 1 is equal to I2 omega 2. Means whatever is the initial angular momentum of your system will be exactly the same angular momentum of system afterwards. We didn't practice any numerical on this. No applications we have seen. Let's practice at least one numerical so that we become familiar with this topic. Angular conservation of angular momentum is an important topic, class. Do mark it as important. Application-based questions do also come from this, and numericals also. Let's discuss one question. Note it down. C class, what does this question say? It says that a man stands on a rotating platform with his arms stretching. Remember one application we did based on conservation of angular momentum, where we had mentioned about the dancers. First, the dancers stretch their arms aside and then they bring their arms closer to their body. That reduces the distance, and so angular velocity increases. This example class, in the last class, no, on last Wednesday, this one. Here, moment of inertia is more because the distance within the, if this is the horizontal axis, this distance is more. So mr square will be more, that is moment of inertia will be more. But when they'll bring the arm closer to their body, all the swinging ballet dancers, this reduces the distance. If this distance from the midline, or you can say horizontal distance, is reduced, angular velocity increases, because if I omega is constant, I is inversely proportional to omega. Remember this concept. Now, so same thing, this is similar to this application only. It says that a man stands on a rotating platform with his arms stretching horizontally, holding 5 kg weight each in his hand. It's like there's a rotating platform, a person is standing, and the person has 5 kg weights in both of his hands. Each weight is 5 kg. Fine. Angular speed of platform is 30 rotations per minute. The angular speed that is present is 30 rotations per minute. Fine. This is the initial, this is the axis, let's say. So this is rotating. Then it says the man then brings his arm closer to his body, right? And then distance changes from 90 centimeters to 20 centimeters. It means right now the distance is 90 centimeters. Then what will happen? Initially, this is the case. Now he brings his arm closer to his body. This is the same rotating wheel he's standing on. Now his arms are closer to his body. So weights are there. And this distance is now 20 centimeter, rather 90 centimeter. Earlier it was 90 centimeter. So this is 20 centimeter. Let's say R2, which is the new radius. Now, moment of inertia of the man together with the platform, right? It means complete moment of inertia. It is taken equal to 7.6 kg meter square, and new angular speed we have to find out. Now, C class for this case we have seen here, angular momentum will be I1 omega 1. This is all about the initial case. I'll give you time to note it down right now. Just understand this. So L1 is equal to I1 omega 1, right? Now see, I1 includes what? I1 includes the moment of inertia of the man, of the platform, plus moment of inertia of the man, correct? Moment of inertia of this entire system that is present. Moment of inertia of this entire system is what? It is the moment of inertia of the platform, as well as it is moment of inertia of the man. Right, this is what it is, moment of inertia of the platform and man combined, as well as the moment of inertia of these masses that are present. So let me write it like combined moment of inertia of platform man plus, see, if this is M1, this is R, we know the value of mass is given as 5 kg and R1 is given as 90 centimeters. For the time being, we'll substitute it at then. I'm writing this one as M and this one as R1. So class C, moment of inertia on the right hand side will become MR1 square. And for the left side, for the right side, it will become MR1 square. So total moment of inertia for these blocks, it will be 2MR1 square. So this is moment of inertia. This is just moment of inertia, IP, that is man plus platform, plus these two masses that are present into omega 1. This is your first equation from the First half of the question. Second half of the question says, see, L2 will be what? Moment of inertia of platform and ma'am will be there. Plus the distance mass is same, but distance is new 20 centimeters. So we'll not take this as R1. We'll take this as R2. So 2m R2 square into omega 2. From here, omega 2 is only unknown. Rest of the things are known to us. And see, no external torque is acting in our system. So L1 will be equal to L2. Now you can equate both these equations. And when you equate these two equations, see, IP plus 2mR1 square into omega 1 is equal to IP plus 2mR2 square into omega 2. From here, omega 2 is unknown to us. Rest of the things is mentioned in the question. See, IP, that is man plus platform, is given as 7.6 plus 2 into mass is given 5. This is 90 centimeters, so we'll use it at 0.9 meters. So that becomes 0.9 square. Omega 1 is given as 30. 30 rotations per minute is there. Again, IP 7.6 plus 2 into 5. And this time R2 will take it as 0.2. So this becomes 0.2 whole square into omega 2. So from here, you can find out the answer, which will be in rotations per minute, because this is in rotation per minute. That you can solve later on and let me know whatever answer you're getting. Like this, you can get questions, numericals also from angular momentum. Quickly note it down, class. Any doubts you have, please let me know. one topic, one small topic that we have before we start with rolling motion. One small topic. See, let's say any random shaped body I have taken. I'm not defining it right now. This is just random shaped body. Center is here and center rotational axis is this. Let's say mass of body is this, and this is the separation from this point to the axis of rotation. Now, there is one topic known as radius of gyration. Radius of gyration is also said, radius of gyration also you say. So, it is defined, it is always defined about its axis of rotation. So, let me define you. It is all, just remember one thing. It is always defined about its axis of rotation. So, it can be defined as the distance, see here, it can be defined as the distance from the axis of rotation, right? From the axis of rotation at which if whole mass of body were concentrated, its moment of inertia about the given axis is given. As in, here at this point, we are taking the center of mass, you can say center of gravity, you can say, or you can simply say where whole mass of body is concentrated. So from that particular point to the axis of rotation, that separation multiplied by mass. All right. So it can be defined as the distance from the axis of rotation at which if the whole mass of the body was concentrated. This definition we have already seen. If whole mass of body was concentrated, same thing is here. Its moment of inertia about the given axis means this only, this axis only. About the given axis would be same as with actual distribution of mass. See what is meant by this last statement. Basically, it says that moment of inertia will be same. So moment of inertia's formula is what? mr square. Here radius, we take it as k. This radius of gyration, this is k. So this becomes mk square. Now for any body, you know what is the moment of inertia. So you can calculate the radius of gyration. For example, if I give you a question, I have made you write all the moment of inertias, remember? So using that only, those diagrams for solid sphere, for hollow cylinder, for disk, for an axis perpendicular to the ring, all these. Suppose if I say calculate radius of gyration of a disk of mass m and radius r. Fine, this is what is given. So moment of inertia of a disk we already know, and I have told you when nothing is mentioned, it means this perpendicular axis only. So for this axis, moment of inertia of ring is mr square by 2 and formula of radius of gyration is mk square. Equate both these, mr square by 2. How much answer you're getting? 58.87 RPM. Okay, yeah, Tarif, I don't remember the answer. Anybody else who gets the answer, please cross-check. Tarif is getting 58.87 RPM for the first answer. Okay, Good, Tarif. It is you have found the answer, which is equal to mk square. So mass cancels. Radius of gyration comes out to be r divided by root 2. Now this you can take for any figure if you want. Let's say one more question. Let's do. Calculate radius of gyration for sphere of mass m and radius r. Now, yes, remember what was the formula of it? Formula for sphere. And see,
2 by 5 mr
yes, correct. For solid sphere, it was 2 by 5 mr square. Good. Just make it solid also for specification. So, yes, good, Terry. So, this is 2 by 5 m r square. And we know moment of inertia is mk square. Now you can equate it. 2 by 5 m r square is equal to m k square. Mm cancelled, k comes out to be r under root 2 by 5. So here this was the radius of gyration, here this is the radius of gyration. So this is actually not a new topic, nothing new, or whatever you've studied for moment of inertia, just equate it with this. Clear? Yes or no, class? Understood or not? Only theorem. Apart from theorem, what about others? Okay, okay. Note it down, then we'll start with rolling. Okay, you are also getting 58 RPM, no? Right. So both of you, Tarif and Abdullah, you're getting the same answer only. So I think this will be the answer, 58 rotations per minute. Good. So only Abdullah and I think Tarif has submitted their assignment. Apart from you both, are all of you submitting the assignments?
Ma'am, I just can't see the assignments on the portal.
You're not able to access this theory. Okay. I'll just talk to them. Anybody else who is not able to access the assignments? Please let me know.
Ma'am, me as well.
Iram, still not. Okay, Iram. Now, class, rolling is basically, let me tell you, rolling motion. So this is a small topic, but it can be confusing. So pay attention in rolling motion. Like radius of gyration was very simple. No, you just had to remember moment of inertia and equate it with mk square, and no other question can be possible from it. Now, C class, you have studied translation motion. In the initial lessons only, we have studied translation motions. Other students like Tereem, Tarif, Jania, you're having the backup class also. There also we were studying about translation motion only, where displacement used to occur. Right. So in case of translation motion, what will happen? This is the center point, this is the bottommost point, and this is the uppermost point. All right, these are all these points. Yes, Yusuf, you have joined quite late in the class.
Yes, ma'am.
Okay. Now, C class. So, Yusuf, we are on rolling motion right now. Radius of gyration and a question on angular momentum we have completed. That you can take video lecture from. Now, see, center of mass we have studied class. So, let's say let me assume VCM is the velocity of center of mass. Fine, this is the center of mass. Now look here, this is point A. So when the body translation means what? Moving forward with certain velocity, with certain acceleration, seems simply moving forward. So here, this component, let's say this is A, this will be moving with velocity VCM. This is the point that I have chosen for center of mass. This particular point, this will be moving with velocity VCM. This is, let's say, O, and let's say this is B. This will also be moving with velocity VCM. Plus, you have in this lesson, in this entire lesson, we were just focusing on rotational motion only. So here you will have rotational motion. Now here what will happen? In rotational motion, you don't have VCM, that is the linear velocity. You don't have, let's say the radius is R. Again, I'm taking all these points. A point, O point, B point. If radius is R, and let's say this is rotating with angular velocity omega. So at this particular point, remember we did tangential velocity. Tangential velocity was equal to R omega. So here the tangential velocity will be R omega. And at this point, the tangential velocity will be R omega. Why is it backward? Because this is rotation occurring, no? This point, when this point will be having this motion, see here, this point is having its motion. It is coming like this, it is reaching the place of B, then again going back to its position, because this is not translation motion, this is rotation. This is translation, forward, backward propulsion. This is rotational, rotation around the central axis. Both these motion combined, when you add both these motions together, that gives you a complete motion, which is known as rolling motion. So rolling motion is what? Rolling motion is simply a combination of both of the motion. This is known as rolling motion. Here, center of mass will be moving forwards also, as well as it will be rotating also. That is known as what? Your rolling motion. Rolling motion is a combination of translation plus rotation. There's one pure rolling also that I'll tell you later on. First, pay attention to this part. Now see here, if you see, in rolling motion at A point, what should happen? This is point A. Combine both of it. VCM, R omega, both the velocities in the same direction. So here at A point, the velocity at A will be VCM plus R omega. Rolling motion is a new topic, but in rolling motion, you have everything that you have studied already only. Now coming to VB, see, in case of VB, this is VCM and this is VB. Both are pointing in opposite directions. So VB, at this particular point, you have VCM minus R omega, because this is the tangential velocity. And if the direction of omega is this way, then the tangential velocity will be like this. I'll mention this. R omega is basically the tangential velocity. So what I'm trying to tell you, class, is you don't study it separately. You study whatever you have studied for translation motion, for rotational motion. Just mainly focus on translation. You have to emphasize on center of mass. For rotational motion, you have to emphasize on the tangential velocity. Like let's take acceleration case. I think then it will become a little more clearer. This was velocity which we were discussing. Let's say acceleration in rolling. Now, class, this is the first case, translation Here what will happen? Again, 3 points I'm choosing. These are 3 points, just extreme and the middle point I'm taking, because every point is not possible to be dropped on. Right, so that's why I'm taking 2 extreme points so that we can get 2 direction and 1 central point. So same thing, acceleration of center of mass will be moving forward. Acceleration of center of mass, it will be covering its linear displacement, translation motion. Plus, you have rotation, rotational motion we study. So here also you have again 3 points. The centermost point you have, let's say O. Now see, acceleration will come again here. So at this particular, let's say this is let's say R, and centripetal acceleration will be pointing towards the center, right, at every point. Again, tangential to this, at this particular point, A point, you'll get alpha R. Remember, tangential acceleration was alpha R. That's why we have studied everything in circular motion already. This was tangential acceleration. If you're not able to recall it, just go through your notes. This is tangential acceleration. And here, look here, class. Here, this will be tangential acceleration for rotation. When you combine these two, you get rolling motion. And for rolling motion, at the center, here acceleration of center of mass will be accelerating as well. And alpha R component will also be present. Understood or not? As well as you will have centripetal acceleration also. You will have centripetal acceleration as well. Understood? Centripetal accelerations component will also come. Here, this tangential acceleration as well as the centripetal acceleration. So if you write the net acceleration, no, that will be acceleration of center of mass plus alpha R plus centripetal acceleration as well. Understood? This is how you write velocities and acceleration. Break it into 2 parts, rest of the thing, you know how to do it. Rotation, you know, you have studied rotation. Translation, you know. Note these points down, then I'll tell you pure rolling. Pure rolling we didn't do, no? This has components of both. In pure rolling, you have, I'll give you examples. In that case, the translation and rotation become equal. See class, understand what pure rolling is. So pure rolling, understanding pure rolling, it is not difficult. All of you have, Terry, I think your mic is on by mistake.
Sorry, ma'am.
Okay. I was saying in pure rolling, yes, example I was giving you that if a car is moving on a concrete road, let me write this. I hope you all have written the above part. For example, take this example, a car moving on a concrete road. This is example of pure rolling. Now, how can I say? See, just imagine a car that is moving on a concrete road, proper, normal road it is moving on. Now, see, whatever is the translational distance covered, that is exactly equal to the rotational distance covered. Whatever is the translation, all the translational motion is exactly equal to the rotational motion. It means this is the starting point. It is rotating and covering this distance. Let's say because of rotation, this much distance is covered. Let's say this is some 5 meters. For example, let's say, even when it is translating, no, from this point A to B, this distance will also be 5 meters only. Means whatever is the distance covered in translation, distance covered in translation, this is exactly equal to distance covered in rotation. This is what is meant by pure rolling. Now, how can you differentiate it? How can you differentiate this? See, let's say this car is not moving on a concrete road. Same example, let's continue. It is not moving. Rather, the tire is stuck in sand. Let's say in the same example, if tire is stuck in sand. Can anyone tell me if the tire is stuck in sand, the engine is on, car is trying to move, which component will be more? Will it translate more or will it rotate more? Car's tire is stuck in sand. Have you not seen? Let's say on a desert, if a car is moving, sand is everywhere. Car is stuck at a point. So what will happen to the tires? Will the tires move forward? Will they translate? Or the wheel will rotate at its
Keep
position?
rotating.
It will only be rotating. Good theory. C class. Just imagine, no, a car is moving on a sandy road, complete sand desert area, let's say. What will happen? Car will not propagate forward. There won't be any forward propulsion. There won't be any translation. Rather, the car would be stuck at a point only and the wheel will be rotating continuously. So that in that case, what will happen? The rotation component becomes greater than the translational component. Take another example. If the tire skids, very slippery road is there on a very rainy season, let's say, the road is very slippery. So usually at the turnings, the car skids. It means the tire does not rotate that time. Translational component is greater than the rotational component. Now see the difference. These are two cases that are possible. But when these are extreme cases, when rotation is more, when translation is more, if both the distance is covered exactly same, neither translation mode nor rotation mode, that is known as pure rolling motion. So in pure rolling, let's say this is the wheel of the car. Let's take R is this is the center of mass and this is the radius. This is point A. Fine. What will happen? This will become point A, right? This will become point A when the car will rotate. And it is translating also. See, from here it has come at this point. And again, this A point will reach back. Understood? So this entire distance, how can I say translation and rotation are same? See class, A point was here. Now again we are getting A point. If radius is R, it means entire periphery has been covered. Entire circumference of the circle has been covered. Every point on the circle has touched the ground. It means this entire distance is nothing but 2 pi r. So this is exactly the distance that is covered by point in one complete rotation. Distance covered by point in one rotation. So see, velocity of center of mass will be distance divided by the time period that is present. And we have one relation, omega can be written as 2 pi by t. Or we can write t as 2 pi by omega. Substitute in here. VCM will be 2 pi r. Instead of t, put 2 pi by omega. So you are getting r omega back. But this is only for pure rolling. This is only for pure rolling, because if it was not to be pure rolling, we would have not got this exact distance 2 pi r. It could have been any value, rotational component more, something else, translation component more, 2 pi r would be less than it, right? And also class, in pure rolling, velocity of point of contact of body and the surface is 0. It means this velocity, which is exactly at the contact, this velocity is 0. Fine, which is exactly at the contact of it. And work done by friction is also 0. Let's say this is moving forward, or let's say here the velocity is acting. So let's say frictional force is acting here. So work done by the frictional force becomes 0 in this case. And one more thing, class. If a very smooth surface is not there, very smooth, shiny surface is there, then rolling motion is not possible. These are just some points from which you can get numericals, and they're not numericals, theoretical questions. Like velocity at the point of contact, what happens, which component is more translation or rotation in case of pure rolling. Pure rolling term will be mentioned separately. This pure term will be mentioned to you. Otherwise, if rolling is there, you know what has to be done. Understood? Let's say if you are given a random point, even if it is given to you in the exam, this can also be asked to you. Let's say this is the center O. Fine. Radius is R. All right. A point has been given to you. This is point C. This is rotating with omega. Fine. You have to calculate the velocity at C. So how will you calculate? Just the procedure I'll tell you. And something else will also be given. Suppose, let's say, this separation is given to you as R by 3. This separation is given to you as R by 2. Let's suppose. Supposedly, this is given to you. This is some point else. C, let's take this point is also given to you. This point is D. And out of C and D, you are asked to calculate velocity at C. So how will you calculate? Method remains the same, class. R, and you know this is a case of pure rolling. So class, R omega is there. It means velocity at this point will be omega R, radius is R by 2. Here, the velocity will be omega R by 3. Here at this point, this will be omega R by 3. And apart from this, at the center, you have velocity of center of mass. So velocity at this C point will be velocity at the center of mass, because that will be there. That component will be there for C point as well. Plus omega R by 2. Like this you calculate. Understood? Like this you calculate. VCM plus omega R by 2. Clear, class? Like this you calculate it. VC will be VCM omega R by 2. In this manner, you calculate the questions like this only. So pure rolling has theory questions as well. Theory questions come from this. So just keep these things in mind and note down these points. If it comes in your exam, mention all these points in clear words. See class, so kinetic energy in rolling is the last topic for your lesson from this lesson. Kinetic energy in rolling also similar to acceleration and velocity. Kinetic energy in rolling, this will be equal to kinetic energy of rotation plus kinetic energy of translation. So this is again class, this is not difficult. See, why is it not difficult? Because here kinetic energy of rotation. Rotation was what? Half I omega square. Remember? Half I omega square. The analog we had done. Half I omega square instead of half mv square. And for translation, you have half mv square. And make velocity here as the velocity of center of mass, because in this lesson, we are focusing on center of mass. So this is the equation. This is just the equation. Even if you wish, you can write this in terms of radius of gyration also. Radius of gyration. You can write this as mk square. So kinetic energy of rolling, this will become half mvcm square will be there. But instead you can write half mk square. So mass common. So half m you can take. You will be left with vcm square. And here is omega square also, no? Half I omega square. So half m taken common plus m omega, no, k square omega square. This is k square omega square. This is the kinetic energy. And in pure rolling, you know one thing, in case it is a question of pure rolling. So you know in that case, VCM is equal to R omega. Just now we have seen. So see how the formula will look like. In pure rolling, if it is a case of kinetic energy of pure rolling. So here you will have half m VCM square. Instead of this, let's put omega's value. Let's put here omega will be VCM by R. So plus k square. So omega square will become this VCM square by R square. So instead of this omega square, I'm putting this value of omega square, that is VCM square by R square. Why? So here I'm taking half m VCM square common. 1 plus k square by R square. This is kinetic energy in pure roll. So these are some formula noted down class. This is all. One numerical we'll practice on this topic, and this will end this. So in the next class, you already have announced that you have a test of center of mass. So please prepare that topic. A short test, I'll have it within the class itself. And we'll start with a new lesson as well. This is an important question. And it's a very basic question. And in most of the school papers, this question gets repeated. So you have, let's say, an inclined plane. Let's take. All have the same mass, same radii. So from here, let's say it is dropped. And to this point, it must be inclined to some angle theta. And here, the bodies are reaching. And what are the bodies? A disk, solid sphere, and a solid cylinder, right? Let's say this height is h. Now we will use conservation of energy. Here we will use conservation of energy. We have seen this in work, energy, and power. What happens here? Here, all the potential energy that is present will be converted into kinetic energy at the end, right, class? So potential energy will be mgh, and kinetic energy, just now we have studied that this won't be just half mv square. We know that these bodies will rotate also. So it will be half vcm square 1 plus k square by r square. So mass gets cancelled. VCM will be, see from here, this will be under root because it was square. So this 2 will get multiplied with this GH, so 2GH, and this whole term within the in the denominators 1 by k square by r square. This will be the formula. For now, then start one by one. Start with disk first. So see, for disk radius of gyration also we have calculated r by root 2. For solid sphere also we have calculated. That will be k will be r 2 by 5. And what else do we have? Cylinder. So cylinder, it will be same as that of disk. Solid cylinder and disk have same r by root 2. Same thing like this we have. Now see, for every of these, you have to put in the values of it. So here you'll put the value, let's say VCM, you will keep it. So it will be 2GH for disk, let's say, it will be 1 plus r square by 2r square, because this is k square with an under root. So r square gets cancelled. So that becomes 2GH by 3 by 2. So that will be 4GH by 3. Like this will be the velocity for disk, and so on. You have to calculate and then see whatever has the highest velocity, are the velocities equal or whatever it is. Fine, like this you have to solve this question. So rest of the parts I'm leaving it. You can complete this. Note down this first because time is not left. Note down this quickly. Any doubts you have from this lesson, please let me know. Next class, we'll have a very short class test and we'll start with the new lesson also. Also, I've received the assignments of Abdullah. I remember Tarif also, I think. Tarif, you have also submitted no assignments?
Yes, miss.
Yes. Tarif also I have received now. So there was error, some technical errors because of which I was not able to receive the assignments which you people were submitting. And rest of you who are not able to access the assignment, I'll talk. Waziha, you are able to receive the assignments in the app. Waziha, Talha.
No, ma'am.
Okay, Waziha is also not able to receive. Talha?